Today we are going to talk about the binomial distribution. This is the first discrete distribution that we are going to see, and I hope that you remember what does discrete variable means in probability. So here are a couple of examples that could be used to describe the binomial distribution. The first one says, suppose that you have a production line and each item that leaves the production line could be either defective or non-defective. So before we move on to the second example, let's see what this example actually is telling us. First of all, see that the item could be defective or non-defective. So you have just two possible outcomes. And the second thing that you could notice is that you are talking about several items. So you are talking about an experiment that happens several times. So you have different trials. It doesn't say here, but you need to imply or you need to have the assumption that the items are independent. So you don't have any impact on the second item if the first item is defective or is non-defective. So the items are independent and you should be able to verify this characteristic. The other thing that we see here is that each item have some probability or should have some probability. So I'm going to write it here. We have different trials. In this case, we are going to note this as n, so you have n trials. You have two possible outcomes. In the case of the production line, we are talking about defective or non-defective. The trials are independent. And we talk about some probability. Probability actually of success. So these four characteristics, you should be able to verify these four characteristics in every problem where you are trying to apply the binomial distribution. So let's take a look at the second example. It says here that each shot in a sequence of firings at a target can result in a hit or a miss. So you have several trials here. You have n shots. It could be 10, it could be 20, it could be 3. So you have n shots. We can assume that they are independent. So it doesn't matter if the first shot was a hit or a miss. The second one has the same probability of being a hit or a miss. You have two possible outcomes, hit or miss, and you have some probability of success. So you could see that actually you have the four characteristics here. When we talk about two possible outcomes, this can be done with more than two possible outcomes. For example, suppose that in the production line, the example of the production line, you could have the product being defective with a major problem. It could be defective with a minor problem, or it could be non-defective. If you are just interested in the non-defective items, you could actually have these two group as one outcome and just have the other outcome as the outcome that is success, that means success for you. So for example, you could have this as the success with some probability and this other here as the failure. with some probability. Of course, these two probabilities should add 1 because you're talking about probability of just two possible outcomes. So here are the properties. We talk about these properties with the examples. The binomial experiment consists on a fixed number of n trials. So we are talk about this n identical trials. Each trial results in one of two possible outcomes, success or failure. We talk about the way that you could describe more than two outcomes. We have probability of success in a single trial equals P, and then you have the probability of failure Q, that it's 1 minus P. This probability remains the same from trial to trial. The trials are independent, and here we talk about the random variable. So the random variable in this case is a discrete random variable, and it is going to be used to describe the number of successes observed during the n trials. So this random variable, it's going to be from 0, because you could have 0 successes in the trials, up to n, because you just have n trials in the whole experiment. Here is the density function for the binomial distribution. So see that you have some items here. You have this notation that it's used to describe combinations. So this is a possible combination. Then you have the value of P and then the value of Q. Note these coefficients here, and note that y goes from 0 up to n. Of course, the probability is between 0 and 1. And let me explain why this binomial distribution has actually this description. I'm going to do this with a little experiment here. Suppose that you flip the coin. You flip 3 times the coin. And I'm going to use this. I'm going to use the black dot here to describe the the head, if you get heads, or the red one if you get tails. If this is a fair coin, what is the probability of getting heads? Of course, the probability of getting heads is 0.5. So let's do this. Y, it's going to be the number of heads in n trials. And let's suppose that I flip the coin 3 times. So if you flip the coin 3 times, you have n equals 3, because these are the trials. And then we have here P, 0.5, and that's it. Actually, you just need P and n to describe the whole probability. So what are the possible outcomes for this experiment? So you could have, for example, head, head, head. In this case, y equals 3, because you have 3 heads in n trials. However, you could have, for example, head, then you could have tail, then you could have head. So in this case, y equals 2, because you have 2 heads in 3 trials. But this y equals 2 could also happen if we have here head, head, and then tails. Or if you have first the head and then, the tails and then head. So if you see, these three outcomes correspond to the same y equals 2. You could also get, for example, head and then 2 tails. In this case, y equals 1. But also, you could have head, tails, head, y equals 1. Or you could have tails, head, tails, and this would be y equals 1. For y equals 0, you just have one option, getting the tails, and the tails. And this would be y equals 0. You see that y comes from 0 to n, 3. However, there are some outcomes. Y equals 1, for example, has 3 possible options, and y equals 2 has also 3 possible options. The best way to count these options are actually with the combinations that we describe here. So when we have the combinations here count for these outcomes here and also for these outcomes here. This is a small example. So you could actually do all possible outcomes like here in the example that I just made. However, it's going to be harder if you have, for example, 20 trials, no? N equals 20, then it's going to be hard to count them. So that's why we're going to use the combination. So the first part, the combination, is the way to count these options. Then, if you take a look here, for example, in the first one without the combination, this is P, probability of y equals 3. The formula says that we have n and then we have y here, and then you have the probability of success. So if we don't follow the formula, you should be able to note here to get the probability, because you would have 0.5, the first one is ahead. Then the second one, since they are independent, you can multiply these 2, and then the third one. And then you don't have any probability of failure because you don't have any tail in the first case. So this could be simplified as 0.5 raised to the power of 3, because we want 3 successes here. And then the 1 minus 0.5, that is the probability of failure, it's n minus the number of successes. So this is 0.5 raised to the power of 0. So that's how we are going to use the formula. So for example, for y equals 2, the formula would say 3, that is the number of trials, then how many successes you want. So here you are going to count the 3 possible options that you have here. Then this is 0.5, how many successes you want, just 2. And then how many failures, of course you would need 1 failure. No, this is going to add this number here, and this number here is going to add the number of trials, because you are just classifying in success or in failure. So those are the ways that you could get the probability. You can do it with the techniques that we saw in the first part of the course, or you could use the formula. The good news is that the binomial distribution has a formula, so you don't need to start counting on using the other approach that we saw, but you could. As we talk about in the first part of the random variables topic, it's important to describe the distribution with the mean and the variance, at least with those two parameters. The mean, you could use mean or expected value. This is a notation. And the variance, it's v of y. You should be able to remember that you can get the standard deviation with the variance, because the standard deviation is just the square root of the variance. And we have the formulas here. We could verify these formulas with the definition of expected value and with the definition of variance, but we are going just to use them and trust the formula. So if you want to get the expected value of a random variable that has a binomial distribution, you just need to multiply n times p. And if you want to get the variance, this is n times p times q. You remember that in this case, the variance is the same as n times p times 1 minus p. No? Some books have q as the probability of failure, some other have 1 minus p. So let's solve a couple of examples here. So the first one, we're going to do one by one. It says here that a complex electronic system is built with a certain number of backup components in its subsystems. So one subsystem has 4 identical components, each with a probability of 0.2 of failing in less than 1,000 hours. The subsystem will operate if any 2 of the 4 components are operating. Assume that the components operate independently, and we have to find some probabilities here. So the first thing is to verify that this is actually a binomial distribution. So let's see if this is the binomial distribution. It says here that you have a complex system and you have 4 identical components. So think about this, for example, 4 identical components here. It says that the components are independent. These components are actually the trials, so we have n equals 4, we have 4 components, and we have some probability of failing in less than 1,000 hours. Now, this probability 0.2 is a probability of failing. You need to make sure to define y, the random variable, in the correct way. So for example, in this case, they are asking us about the components that last more than 1,000 hours. So we need this to be y, it's going to be number of components that last more than 1,000 hours. So the probability should be the probability of a component to last more than 1,000 hours. So the probability of success is 0.8. So make sure that this definition here, that last, corresponds to the probability of one lasting more than 1,000. You could also use y as the number of components that don't last, so p is going to be 0.2 in that case. And the other parameter is the number of trials, n equals 4. So in the binomial distribution, you just have 2 parameters, p and n. N equals the number of trials, and then p equals the probability of success. So now we can use the formula. It says here for letter A, let me do this one. So we have n, we have here in letter A, the first question says letter A. it says what is the probability that exactly 2 of the 4 last more than 1000 hours. So this is the probability of y equals 2. And the formula said that we have the combinations. Here is 4 and here we have 2. Probability of success 0.8 raised to the power of the number of successes here 2. And then probability of failure 1 minus p raised to the power of 4 minus 2. So you could do this in your calculator and give me the result. So this should give you 0.1536. So this is the probability of getting exactly 2 out of the 4. It doesn't matter if the components that work are the first 2, the last 2, the first one and the third one, or any other possible combination. Then let's do letter B. It says the subsystem operates longer than 1000 hours. So if you remember, the subsystems work if any 2 of the 4 components are operating. So actually we just need at least 2. So in the discrete case we need to sum these options. So we need to have the probability of y equals 2, then the probability of y equals 3, and then the probability of y equals 4. And this is going to be the last term because the variable y goes from 0 up to n. So in this case, the highest value for y is 4. And we are going to use the formula. Of course, the first term you already have it. The second one is going to be the combination 0.8 raised to the power of the number of successes, then 0.2 raised to the complement. Again, remember these 2 should add the value of n. And finally, the last term is the combination here, 0.8 raised to the power of 4, and we don't want any failure. So you can also do this, and this should give you 0.9728. Let me just remember you that you could also do this, the letter B, this way. If you have y greater or equal than 2, this is exactly the same as having 1 minus the complement. And the complement is y less or equal than 1. So this is going to give you the same result if you do this p probability of y equals 0 plus the probability of y equals 1. So here you just have 2 terms. However, in the first option, we already have y equals 2. So this is going to give you the same result, and you can verify this. Okay, so let's take a look at the second exercise here. So this is the first one, this is the other option for the first one. Okay, let's analyze here the second one. Again, let's see if this actually could be modeled with a binomial distribution. It says the probability that the patient recovers from a stomach disease is 0.8. Suppose 20 people are known to have contracted this disease. What is the probability that exactly 14 recover, that at least 10 recover, that at least 14 but not more than 18 recover, and at most 16 recover? So let's see. We have some number of trials. In this case, 20 people. So these 20 people implies the number of trials that we have, n equals 20. Then if we describe y as the number of people that actually recover from the disease, we have the probability here 0.8. We could describe this experiment with two possible outcomes, recover or not recover. And we should have the assumption that the patients are independent. So each patient could have the disease or not with the same probability. So with that assumption, we could use the binomial distribution to get these probabilities. Okay, so let's have it here. So we have n equals, well, let's describe y. So y, it's going to be the number of patients that recover from the disease. So we talk about n, 20 patients, number of trials, and then p, it's going to be 0.8 again, because these two should match. 0.8 is the probability of recovering. So the first question says that exactly 14 recovers. So we have the combination 20 out of 14. P, it's 0.8 raised to the power of the number of successes, and 0.2 raised to the complement here, that is 6. So this is going to be equal to, so this should be equal to 0.1091 here. So let me have it here. And then let's do letter B. B says at least 10. So this is the minimum value, should be greater or equal than 10. So you will need to add probability of y equals 10 plus the probability of y equals 11, and so on until the probability of y equals 20. And you can use the formula for each term, and you should get 0.99940. So that would be the value for the result for letter B. And then let's see letter C. Here we have an interval, at least 14, but not more than 18. So you have y between 14 and 18. So you are going to add y equals 14, so on until y equals 18. And you are going to use the formula and add the values. This should give you 0.8441. And finally, you have letter D. At most 16 recover, so you have a maximum value less or equal than 16. So you could go from 0 up to 16, or you can do it the other way. 1 minus the probability of y greater or equal than 17. You cannot include the 16 here in this part because the 16 is in the other part, so you need to start in the 17. So you can do it both ways. Probably the second one is the fastest way to get it, and this is 0.5885. And actually you can do several combinations here. You could have a maximum value, a minimum value, a range, etc. Most of the times you have to sum. You could use your calculator, you can use Excel, and we are going to see how to do that in after we solve these examples. Finally, let's see the last example here. It says that you have a multiple choice examination with 15 questions, each with 5 possible answers, and only one of which is correct. Suppose that one of the students who takes the examination answers each of the questions with an independent random guess. What is the probability that he answers at least 10 questions correctly? So again, first we need to verify that this is actually a binomial distribution. So you have 15 questions here. So that is the value of n. And then it says here that they are independent. So we can have also the assumption. However, it is not clear here what is the probability of success. So let's think a little bit before we answer that. So let's talk about just one question. So the question has 5 possible answers. However, just one of them is correct. So if you do this at random, what is the probability that you actually get the correct answer just for one question? Exactly. The correct answer, if you are doing it random, you are going to choose the correct answer 1/5. No, because we have 5 possible answers and just one correct. So this is the probability of success, getting the right answer. Now, if we define y as the number of correct answers in 15 questions, then we can actually do this with a binomial distribution. Again, remember that this probability should have the same option, the same outcome that you are measuring with y. No? If you are talking about correct answers, then p is going to be the probability of that correct answer, and you also have the value of n. We discussed the value of n equals 15. So now the question is, what is the probability that he answers at least 10 questions correctly? So y should be greater or equal than 10. And you can do it, the fastest way to do it is to have probability of y equals 10 equals 11 and so on until the probability of y equals 15. And you should use the formula. So you have 15 questions and you select 10 to be correct. Then you have the probability of success 1/5 raised to the power of 10. And then the complement 1 minus p, that would be 4/5. And this would be the value for the failure. So remember, these two numbers here should add 15, that it's the total trials, and so on until you have 15/15, 1/15, this is raised to the power 1/5, sorry, this is raised to the power of 15, and then the 4/5, this is raised to the power of 0. We don't have any failures here. And finally, you should get 0.00011. If we think about it, this is a really small probability. And the reason is that the probability of success, this probability here, it's actually small. Of course, this is because you have no clue about the answer and you are just guessing. Let's hope that you don't do that in the exam.